in the last two lectures, we looked at special functions. We looked at the step function, the Dirac delta function, and then we also looked at gamma function and the error functions. Now, these functions were defined in terms of integrals, okay, and these are very useful functions, and you will see in your advanced physical chemistry courses that these functions appear very often. Today, I am going to change the topic a little bit. Okay, we are going to discuss about spherical polar coordinates. These are again things that you will see very often. Okay, so at least once you should work these things out completely. So today I'll talk briefly about spherical polar coordinates, and I'll show one very interesting application of spherical coordinates in evaluating the value of a gamma function. Let's first work in two dimensions. So if you have x y space, so typically your coordinate system is in terms of x and y, and you write your functions as functions of x and y. Okay. So, any point in space has a certain x coordinate and a y coordinate. Okay. Now, instead of using x and y coordinates, okay, very often we are interested in problems that have a spherical symmetry, so or a circular symmetry. So what you do is you define an r and a theta. Theta is this angle with the x axis, r is the distance of this point from the origin, okay, and you say that r equal to x square plus y square, okay, under root theta. So we see that tan theta, okay, equal to y by x, okay, or you can say theta equal to inverse tan inverse of y by x. Okay. So now so instead of f of x y, we go to f of r theta. So any function of x y is written as a function of r theta, okay, and this is turns out to be extremely useful. Sometimes very often we do integrals. Okay, so when you are doing integrals, integral f of x y dx dy, if you are doing a two dimensional integral, okay, now this is actually equal to integral f of r theta. Now instead of dx dy, you have to convert to dr d theta. So we will have dr d theta, and you will have some object here which is called the Jacobian. Of the coordinate transformation. So what is this Jacobian? Now I won't work out the details, but basically this Jacobian is this is just r dr d theta, and now what about let me explicitly write this as a double integral. Okay. So the first integral is over r and the second integral is over theta. You have to put the appropriate limits. Okay. Now what are the range of values? Okay. So now x and y, they go from minus infinity to plus infinity. Okay, x and y go from minus infinity to plus infinity. R goes from 0 to plus infinity. So r is always positive. Okay, so it is defined as a positive square root. Theta, okay, now theta goes from 0 to 2 pi. So when it goes to 360 degrees, the value of theta is 2 pi. Okay, so these are the range of values of x, y, r, and theta. So this is sometimes referred to as plane polar coordinates. or sometimes it is also referred to as circular coordinates. Okay. Now, this is plane because you are in the x y plane. Now, what happens in 3 dimensions? So, in 3D you get what is called as spherical polar coordinates. Okay. So, here what happens is you have x, y and z. Okay. Now you have some point, okay, whose coordinate is x, y, z. Okay. Then you have this line from the origin to that point. So, this distance from the origin to that point is r, and now in this case your theta and phi have to be defined differently. So, what is done is the angle with the z axis is called theta, okay. And remember, this point need not be in the x y, it need not be at in this z y plane, it can be outside the plane. Okay. So, it can be, in general it can be outside the plane. So, now you need one more variable, okay, to describe it, and that variable is chosen in the following way. So, you project this vector onto the x y plane. So, you see where it falls on the x y plane, and now you look at the angle that it makes with the x axis. This angle is called phi. So, what we did is we went from x y z to r theta phi. So, what are the definitions? So, clearly r is equal to square root of x square plus y square plus z square. Now, if you just drop a perpendicular onto the z axis, so this is the z coordinate. Now, if you want to calculate the x coordinate, so you can do it through these two steps. First, you drop a perpendicular on the x y plane, then you project onto the x axis. So, this is the x coordinate, this is your y coordinate, Okay. So, you can easily see that cosine of theta equal to z by r, okay. And you can also see tan of phi, okay. So, the tan of phi, okay, is basically y by z. Further, you can see a few more things. You can see that what is sine of theta. So, sine of theta, okay, is basically this projection, okay, and that is equal to square root of x square plus y square divided by r. So, now with this you can rewrite you can write z equal to r cos theta, okay, and what you can write is you can write x is equal to r sin theta. So, r sin theta is square root of x square plus y square. So, this implies that r sin theta is equal to square root of x square plus y square, okay. And so oh, I got this incorrect. So, this should be y by x, okay. So, x will be r sin theta cos phi and y will be r sin theta sin phi, okay. So, you can see that y by x is tan phi, okay, and it satisfies this condition, okay. So, this is the definition of the spherical polar coordinates. Okay. Now, you can do various things. So, now if you remember, when we went to functions of x, y, z, okay, we call them as scalar fields, okay. And if you remember, we defined things like divergence of a scalar field, or sorry, the gradient of a scalar field, gradient of f, and we also had a gradient. You can also take a gradient dotted into gradient of f, or del square f, which is, or it is also denoted by Laplace, this triangle of f, which is called the Laplacian of f. Now, if you remember the expression, so we had gradient of f was dou f by dou x into I plus dou f by dou y into j plus dou f by dou z into k. And the Laplacian of f, okay, this was given by dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. Okay. Now, what you can do is you can actually get expressions for each of these. So, if you had f in spherical polar coordinates, okay, so if f is expressed in spherical polar coordinates. So, if you had f of r theta phi, okay, then what you can do is you can write dou f by dou x as, now remember, when you take dou f by dou x, you are keeping y and z fixed. Okay. So, you can write it as dou f by dou r keeping theta and phi fixed times dou r by dou x keeping y and z fixed plus dou f by dou theta keeping r and phi fixed times dou theta by dou x keeping y and z fixed, okay, and you have dou f by dou phi keeping r and theta fixed times dou phi by dou x keeping y and z fixed. So, notice all I did was I wanted a derivative with respect to x of f. So, I take derivative of f with respect to r times derivative of r with respect to x, but f also depends on theta. So, I take derivative of f with respect to theta times d theta by dx. Similarly, it also depends on phi. So, I also take that, and this is the derivative with respect to x. Now, this, if you know this function as a function of r theta phi, you can evaluate this. Okay. So, I will not explicitly write these quantities that are constant, but you should remember that whenever you take derivative with respect to x, you are keeping y and z fixed. When you take a partial derivative with respect to r, or then you keep theta and phi fixed, and so on. What I can write is this, what is dou r by dou x keeping y and z fixed. Okay. So, then you have to write r in terms of x y z, dou by dou x of square root of x square plus y square plus z square. So, this is keeping y and z fixed. So, y and z are like constants. So, if I take a derivative of a square root, so I get 1 over square root of x square plus y square plus z square. Now, I take d by dx of this quantity, that is just 2x, okay, y and z are constant. So, this is 1 over 2i square root of that. So, this is just x divided by square root of x square plus y square plus z square, okay. And you can write this as x by r, but you should be very careful. Okay. So, you can why I mean you should be careful is because x by r is actually, put this in, be careful when you write such expression. The reason is because they are in two different coordinate systems. So, x is in Cartesian, whereas r is in spherical coordinates. Okay. So, writing something like x by r is something that should be done with extreme care. Okay. Using this, I can write the derivative with respect to x, okay, and once I have a first derivative with respect to x, I can also calculate the second derivative with respect to x. So, similarly, we can calculate second derivative x and so on. Okay. So, let me just mention a few things. Okay. Let me just write some of these partial derivatives that appear. So, if you take dou r by dou x, this I wrote it as x divided by r, dou r by dou y will be y by r, dou r by dou z will be z by r. Okay. Now, let us just look at some derivatives of theta. So, what is dou theta by dou x? Okay. So, what is theta? So, we wrote theta as tan rather as cos inverse of z divided by r. Now, I cannot write r, I have to write it as square root of x square plus y square plus z square, okay, and you are taking d by dx. See, I wanted to take a derivative with respect to x keeping y and z fixed. So, therefore, I had to write it in this form. Okay. Now, so this is what you will get for d theta by dx. Okay. Now you have to write the derivative of cos inverse of some quantity. So, it is, so this will give me so derivative of cos inverse is just that quantity divided by square root of 1 minus, now I will have z square divided by x square plus y square plus z square. Okay. And now, I have to take the derivative of this quantity with respect to x. So, what I will get is, so it is, you have something raised to minus half. So, it is, so I will write z divided by 2, and what you have is x square plus y square plus z square raised to 3 by 2. Okay. I have a minus sign here, and then you have to take the derivative of x. So, you will get twice x. Again it looks very tedious, okay, but you will find that lot of things will cancel. Okay. So, for example, the x, so once we have done this, I will just replace this by r. So, this is z by r, this is minus z by r cube. Okay. So, I will have z square by r square, and then I have an x that is hanging around. Okay. And then what do I have here? Now, I have x square plus y square plus z square minus z square. So, that is x square root of x square plus y square, and then divided by square root of x square plus y square plus z square, that is just r square. Okay. So, I will have r divided by r. Okay. So, what do I get? So, I finally get the expression is z square x divided by r square root of x square plus y square. Okay. So, and you can write this in a slightly different way. So, if you realize that z by r is, so z square I can write as r square cosine theta. So, I will be left with r cos square theta, and then x over x square plus y square is nothing but cos phi. Okay. So, I will have r cos square theta cos phi. Okay. So similarly you can calculate all derivatives can be calculated. Right. And you can write Laplacian and we can write an expression, okay, expression for del square f is equal to dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. I can write this in the entire thing in spherical polar coordinates. Okay. So we can write this in terms of dou by dou r, dou by dou theta and dou by dou phi. Okay. So we can write this expression. Okay. Now if you work out this expression, okay, it's quite a long expression and I will just write it. Okay. So you have to go step by step, you have to calculate each derivative individually and you have to work it out. Okay. So I will just write the final expression. Okay. So this is something that you will use quite often in problems in quantum mechanics. So I will just write the expression for del square, okay, which is written as dou square by dou x square. This is written in an operator notation, dou z square. So this is in Cartesian. When you write the expression for the Laplacian in Cartesian coordinates, it just looks very straightforward. It looks like dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Now when you write it in spherical polar coordinates, the expression is considerably more complicated, okay, but you can work this out. So you have a dou square by dou r square term, okay. Then you have a term that looks like 2 by r dou by dou r, okay. Then you have a 1 over r square sin theta and you have dou by dou theta of sin theta dou by dou theta, okay. And then you have a plus 1 over r square sin square theta dou square by dou phi square. Okay. So this is the expression for Laplacian in spherical polar coordinates. Okay. And this I have written it like an operator. So I have not shown the function that it is acting on. Okay. I have not explicitly shown the function. So I have just shown it like an operator. Okay. And this is the operator that corresponds to the Laplacian. Okay. So if you had a Laplacian of f, okay, then what you would write is Laplacian of f, okay, then you will have f in all these places. So the derivative will be of f. So here you will have one derivative and then you have to take the derivative of this whole thing of sin theta df by d theta. Here you will take a second derivative with respect to f. Okay. Now this is a very useful expression that you will see quite often. Another thing that will appear very often is what is called the Jacobian. So Jacobian, okay, so this appears in suppose you have integral f of x y z dx dy dz, okay, it is a 3-dimensional integral. So you are integrating over x, y and z. Okay. So then I can write this as instead of x, y, z I can write this function of r theta phi, okay, and I have the 3 limits. Okay. Now what I will have is instead of dx dy dz I will have dr d theta d phi times some quantity which is called a Jacobian. Okay. So this quantity what appears here is r square sin theta. So this is the Jacobian of transformation. Okay. And now, so this integral will be replaced by this. Now, the range of values so x, y, z go from minus infinity to plus infinity. Okay. Now, r goes from 0 to infinity, theta goes from 0 to pi, okay, and phi goes from 0 to 2 pi. Okay. So, now initially it might seem a little confusing why theta goes from 0 to pi and phi goes from 0 to 2 pi, okay. But we can see this geometrically, or so if you have your coordinates x, y and z, okay, and we took some point, okay, and this point might be outside the y z plane, okay, and we said that this angle is theta, okay. So, there is this cone that goes like this, and so anywhere on this cone the angle with the z axis will be theta. So, whether you are here, even if you are here at this along this line, the angle will be theta. So, here also it will be theta. So, now theta can only go from 0 to pi, because once you reach pi, then you are pointing along the negative z axis. So, when theta equal to pi, you point along the negative z axis. So, here theta equal to pi along this direction. Okay. And if you go more, then as I said, theta is only defined with respect to the z axis. Okay. So, you cannot go more than pi. Now, what about phi? Phi is defined in the x y plane. Okay. So, this is my phi, okay, and clearly phi can go all the way from 0 to 2 pi. Phi can go all the way from 0 to 2 pi. Okay. So, therefore, we emphasize that theta goes from 0 to pi, phi goes from 0 to 2 pi. Okay. So, phi is called the polar angle, theta is called the azimuthal angle. Okay. So, I will conclude this lecture here. So, we have learnt about spherical polar coordinates, and I have spent quite a bit of time discussing this. Okay. What happens is you do spherical polar coordinates, if you learn it very well, then learning other coordinate systems like the cylindrical polar coordinate system or elliptical coordinates becomes very straightforward. Okay. So, what I have tried to show you is I have tried to show you some of the things that you learn in spherical polar coordinates, okay, and there are a lot of formal derivations which I have skipped, okay, but at least you will be familiar with spherical polar coordinates after this, okay, and you can whenever you have to learn some new coordinate system, it will be relatively straightforward. Thank you.